This is the first day of August. Have kind of a quick one tonight. Let's see. What have we got ahead of us? Let me look at my schedule here. See, we have Thursday tonight and Tuesday and Thursday. So we have two more class meetings. And I believe that the 8th, let's see, the 8th, let me double check this one. On the 8th, go to my academic master calendar. And let's see, that would be this one. August 2019. Academic calendar. Okay. Fall, okay, I guess I need to back up one. This one, summer 2019. Okay, August 12th through the 13th, the 10-week summer finals are August 12th through the 13th. So that puts us, let's see, so we have first, the 6th and the 8th. So after tonight, we have two more class periods, and I'm going to wrap up on the 6th, and then on the 8th, I'm going to kind of bridge into the next class period. Our final exam is the officially August 12th. Okay, so August 12th, 13th, 14th. So officially we have August 13th. Now we're going to have, remember what I said is that the final exam will be optional. So we have two more class periods after tonight. Okay. So tonight we are in the module module 13, which I've ordered. Select out creating and maintaining indexes. And we're going to talk about what is an index. And what I'm going to do right now is I'm going to discuss the idea of an index and how do each of these do this. But the first thing I'm going to do is I'm going to play a quick little video. And while I'm playing this video, because the video is available online, I'm not going to bother recording it. So I'm pausing the recording. Pausing recording now, and you can go over here and look at the video. I don't need to play it for you if I've got it recorded. Pausing recording. So I'm resuming the recording now, and I've been told that the audio on the video isn't working. So I'm going to let you guys watch that. Let me get out of this thing if I can.
May I interrupt you?
Sure.
Because it's just a quick question about the assignment that we should be turning in today, the Module 11 exercises. So the case and the if we did not cover, correct?
I don't believe we did. No, we haven't, and we sometimes I do and sometimes I don't. That I have not in this semester. It is not a bad one. It is unique to uh, SQL Server.
Okay. Well, and I read the note that it would be good for us to learn it. I just didn't know if we should be
Yeah,
turning, trying to turn that part in, and if we needed to worry about it as of yet for test two.
I'm not. No, we want not going to worry about it for test two by any means. It's not there. Okay.
Thank you.
Okay. Let's see. Have I started the recording? Okay, I've started the recording again. I regret that the two Ronnies did not work out the confusing library. Do go watch it. It's kind of funny. And what they have is called is an odd indexing scheme. And so they have their library, it's indexed by the color of the book, by the size of the book, and things like that. And it's rather a silly idea. So they call it the confusing library. Go to the next. And in a library, well, our book is somewhat weak on indexing. And let me see if I can. Database indexing. Database indexing, we talk about indexing makes the query fast. Let me see if I can get to something here. Okay, an index. Think of a library index. When I was a kid, I had to walk to school 2 miles through the snow, and indexes looked like this, and they were card indexes in a library. And you went to this card index and you looked up the book that you wanted. For example, there were 3x5 cards and they were in the index, and one card for every book in the library. And so there were actually 3 of them, and there still are. Um, a library had a title index, an author index, and a subject index, the blue index, red, yellow, and blue. So if I wanted to look up a book by title, I would first search the title index, and then I could go straight to the book in the shelving area. I know exactly where it was. Similarly, if I wanted to find the author's textbooks, I could go look up the book by author, and I would find a list therein. I would find a list of all the books by that particular author. And so I might come up with 5 or 6 books by that author, and then I would take my list and go out to the shelves, and I would then search for each book in order. Similarly, I could search by subject, and I could find books, for example, by if I wanted to find a book on whales, I would search by subject, and therein I would find a number of books, and then I could go out and look up each one that I wanted by where they were on the shelves. So I could search by any of those 3, and those 3 are still the big ones: the title, the author, and the subject. So let's look at these examples. What if I wanted to find the books that contained 376 pages? Huh? Well, I don't have an index on the number of pages in the book. Why don't I have an index on the number of pages in the book? I'm sure I have that in my information. I'm sure that I know how many pages are in the book. Why not create an index on the number of pages? Well, nobody ever searches for a book that has 376 pages. Doesn't happen. Consider the librarian has to update all 3 indexes. And these aren't free, and the librarian has to work with them, and nobody cares how many pages the book has. I don't care whether it's got 376 or 3,000. I'm looking for a particular book. I'm not interested in the number of pages. Example 2. What if we could judge a book by its cover? Why not build an index on the book's cover's color? Well, in the first place, nobody cares. How many different colors do we have? Oh, 5 or 6. It's pretty likely there will be at least one book of any given color on every shelf of the library. This will be a waste of time. If we're going to have to go, if I search by this index, I'm going to get 20 to 25% of the entire collection. It would be a whole lot easier just to take my little cart and go through the shelves from start to finish. With me. So nobody cares about the number of pages. The color, well, probably nobody cares about the color either, but the color is, I'm going to get too many books. If I say I want books with red covers, I'm going to get way too many of them. Sometimes books come with abstracts, a one-page synopsis of the book. Should we index the abstract? Now, how much information is that? An abstract is probably a page or so of information. I would have to reproduce the entire abstract on the index card. This would cost a lot of storage space. Okay, so I don't want, for an index, I don't want a very big field. I want something small, kind of like a primary key. Example 4, the library system has to track books being checked in and out. So I have a field that tells me whether it is checked in or checked out. Do I want to index that? Every day, that field is going to be changing. Every time somebody checks it in, checks it out, that field changes. And I don't like, for an index, I don't like data that change radically, okay? What does the librarian have to do? It's rapidly changing. The table is important to the function of the library, and I need something that is relatively static. General guidelines, okay? 1, don't create an index for fields that nobody cares about, fields that are searched infrequently, or small tables. They're wasting your resources. Now, if you go look at Access, your options are, do you create an index? The answer, yes, no. The answer is Access by default creates indexes, but we don't like indexes unless they're going to be used. Do not index fields that have very few, this is the important one, I think. Do not index fields that have very few distinct values. What do I mean here? Consider a database that has all of the people in Frisco. Now, consider their zip codes. Should we index their zip codes? Well, we probably aren't going to be searching by zip code very often, but let's say we were. If we were, how many zip codes are in Frisco, Texas, do you think? Would I be far out of line if I guessed 20 or so? Do you think?
I have no idea, but I see where you're going with it.
Yeah, maybe 20. So I'm going to guess 20, and I would just say it's right. Okay, in that case, I'm going to get probably 5% of the database anytime I search on the on a zip code. So if I say I want all of the zip codes of 76210, wherever it is, I'm going to get a big chunk of people. And I would do better not to fool with an index, because I'm going to have probably one person on each page of my data. We try to build indexes on fields that are as small as possible, because the values have to be reproduced, and we prefer to index static data. For example, here's my example. Write to the Social Security Administration and say, hey, I'm tired of my Social Security number. I'd like a new one, please. They're not going to give you a new one because that's considered static. So we basically, our primary key is very definitely an index. So don't index fields that we don't care about. Don't index fields that have very few. For example, male, female would be a terrible index, because anytime I search on that index, I'm going to get half of the database or so. That's terrible. So we call that a low cardinality. If we get over 5% of the database, it's a poor candidate. So what would make a good candidate for an index? Your phone number would be a good candidate. Your date of birth would probably be a fairly good candidate. Your street address might be a good one, but the problem with it is that it would probably get to be a little bit too large. I like them as small as possible. I like one number. I like something like your driver's license number for that. And I like something that will never change. Okay. Indexing. Okay, index table. What am I doing here? I don't forget what I'm doing here. Demo 1, Demo 2, Demo 3, constraint, primary key, Demo 1. This one is a primary key, so Demo 1 is a primary key. Do not build an index on a primary key. Do not create an index on a primary key. They already exist. Second one, do not build an index on a field that is unique. I don't believe we have seen this constraint unique, the unique constraint yet, but here it is anyway. Constraint unique, Demo 2 has to be unique. Now, think about it. If Demo 2 is unique, every time I insert into Demo 2, I have to search that whole table to make sure there isn't something in there that it isn't already in there. Therefore, the database will build an index on it to speed up searching. So do not build an index on a field that is constrained as unique. Primary key. So when we create an index, there's nothing to it. It's just like this. This is how it's done. Create index. Well, thought I had it there. Create index. Give it a name. The name must be unique in the database. There are different thoughts on how to name it. My particular thought is that I tend to have named mine with the ending in index, so demo index. Others will tend to name theirs IDX. Okay, so they will tend to prefix it with the word IDX, and I think this is the one that is kind of taking, becoming more prevalent than mine of saying demo index. They are prefixing it with IDX underscore and then the name. So by looking at it, the name IDX, if it has IDX as the first three letters, it is an index. The index has to be unique in the database. You can't have two indexes that are the same. Now, this is really all there is to it. and boom, it's created. Create index, give it the name on, and then you give it the field on which it's created. You can create it on more than one field. Okay. In that case, if I specify those two fields in a search, it will use the index, and the database is very good about using its indexes. The problem with it is if I try to create it, if I create an index on a primary key, then I'm going to have two indexes on the same field. If I create an index on a field that already has an index, for example, demo 2, then I will have two indexes on the same field. Okay, so reviewing the indexes, it's frequently searched. Is it frequently searched? And here I make a statement and I say foreign keys are usually, pretty much always, kind of like always, but I'm not going to say always. Foreign keys are usually good candidates for an index. They're almost unique. You're not supposed to say almost unique. It's either unique or it isn't. Almost unique means that, gee, you might have a duplicate somewhere, okay? For example, if I have a group of students for, let's say all of my students in all of my classes, and I probably wouldn't have your birth date. I don't have that in my database. But if I did, what are the chances that someone else would have your same month, day, year of birth? Fairly low. I'm not going to find that happening very often. So I can say that your date of birth, month, day, year, is pretty close to unique, although I might have a duplicate that would probably be a fairly good index if I used it a lot. A small scalar value. Scalar means that like a number. A number is scalar. Something is scalar if for any two values, one is greater than, less than, or equal to the other one. So something like a number, a date. Your name is scalar because your name is either greater than, less than, or equal to any other name. So a small scalar value. I like your name. I like a date. I like your social security number. I really like that for an index. In fact, if I have your social security number, I'm definitely going to create an index on it because I'm going to have to reproduce it. Static data, I don't like anything that changes for my indexes. Okay, here's the other one, not a primary key and not a unique field. So these are these things make good indexes, and if it meets these criteria, then I would probably consider building an index on that field. Questions?
Could you give me an example of the opposite of a scalar value?
Opposite of a scalar value would be your picture.
Got it. Thank you.
I have no way of comparing your picture to anyone else's picture and saying it is equal to, not equal to, greater than, less than. It's just a picture. Your digitized fingerprint, your signature digitized, those are not scalar. Your social security number is scalar. Yours is either greater than, less than, or equal to mine. Your date of birth is either greater than, less than, equal to mine. Your name, we can alphabetize our names and I can put it in a list and and sort them. So the answer is, can I put it in a list and sort them and have it make sense? Some people would argue that your social security number isn't because it doesn't make any sense to sort them, but I can sort them just fine. So social security number is scalar. Okay. Greater than, less than, equal to.
Thank you.
Okay. Oh, here we go. I never know how much to do of this. When you create an index, I'm not going, I can get bogged down in this, and I can be bogged down in this for the next however many classes we want to have. B-tree. When you create an index, you create what we call a B-tree. A B-tree is a search tree. Basically, you come into this guy and I am searching for something, and this is just going to be a real quick introduction to it. If you go into computer science, you're going to get to write one of these things before you get out. And basically, I come in here and I'm searching for some value. Let's say, I don't know what I'm searching for. I'm searching for something so that's indexed on this number. So 19 is my search key. I'm searching for a 23. Now, is it less than or equal to 19, or is it greater than 19? If it is greater than 19, I follow this address, this disk address, to another one. Is it, let's see, what am I looking for? 23. Is it less than 24? It is less than 24, so I follow this one down here. And here I find a node, 19, 20, 22, 23 is not here. I did not find it. Had I been searching for 22, I would have found it. Okay. 24, is it greater than or equal to 24? Follow this pointer down to this disk page, and therein I find 24, 27, 29. So basically the idea being that I find my key, I'm searching for something, and I find it with one disk access, and probably this one is in memory. So I follow this one, pull up one more page, one, and then one further page, and I have the one. So with 1, 2, 3 disk accesses, I find what I'm after. And so the whole idea is to minimize disk accesses. And if you find that complicated, a B+ tree is a monstrously complicated data structure, optimized for searching a disk drive. A detailed discussion is well beyond this class. The video is worth watching, I guess. Each node in the tree is really a disk page. It's really 4 kilobytes. So this is a 4 kilobyte disk page. This is a 4 kilobyte disk page. Let's see if it runs. I guess it runs. I'm going to guess it runs. Okay. Yes, thank you. Okay, if I can get back to where I was. Okay, anyway, if you want to watch this, I think it's worth seeing. It is a very complicated structure. Estimating the disk needs, I don't think I'm going to do this. Estimate the size of the table. I can estimate the size of the table by taking all of the records. How many records do I expect to be in that table? And I have to be able to come up with some kind of an idea of how many records will I expect to have. And there is no way to do that besides looking at your business plan. How many customers do you expect to have? People will tend to overestimate or underestimate that frequently. So I take the size of a customer records, I add up all of the fields, and I give it a 10% overhead, a rule of thumb, then multiply it by the maximum number of records I expect. Thus, 500 bytes for a record, typical. 1,000,000 records is a fairly small. Thus, I would need 500 million bytes. Oh, well, not really a big table, half a gigabyte, I guess. Now, with an index, how big will this index be? If we estimate the size of an index, we have to think about how big is the key. So the key is important to us. If the key is 36 bytes, now I don't know that that's good. I'm just guessing. How big is a social security number? Social security number would be, if I were storing it as a text string, would be about 10 bytes. So I'm just going to say a name, for example. A name would be about 36 bytes. Add to that the 4-byte disk address, and we have 40 bytes per entry. Each node is 4 kilobytes. So each of these guys, each one of these disk pages is 4 kilobytes, or about 4,000 bytes. We can get 100 values into each node. In the second level of the tree, we have 100 nodes, 10,000 possible values. At the third level, we would have 10,000 nodes, and we would be able to index over 1,000,000 possible values. So with a 3-level tree, we would get fairly large. We would get 1,000,000 possible values in our tree. How big would that be? We would use up about 41 megabytes for that. So an index isn't free. An index is going to cost us. How much will it cost us? We have to figure out how big our key is, how many nodes we're going to have in our tree, and do the multiplication. 41 megabytes isn't a huge cost, but it's a cost. If we compare the time of access in our little half-gig table, not particularly big. There are about 125,000 disk pages. If I have a 5 millisecond access time, which is pretty standard, and I have to scan the whole table, I will have 625 seconds or something like that. 625 seconds is about 10.5 minutes. So if I go into this, this half gigabyte table, and I search it, it's going to take me about 10 minutes to search it. On the other hand, if I have an index, given that I have chosen it wisely, I will get to my single record in less than 0.2 of a second. Okay, it makes a big difference. So anytime you're searching, you want to search on a primary key because you've already got the index set up. A 3-level B+ tree, pretty normal. Huge difference. It makes a huge difference. Okay. When we index, here's the points, and these are the ones that I'm going to want to hit on. Choose a field that is frequently searched. Okay. If it's a foreign key, consider the foreign key as the candidate for an index if it meets the rest of the criteria. There's one of them in there that I gave you that does not. I believe that the terms, excuse me, the terms ID does not meet one of those criteria. Foreign keys are generally good candidates for an index. Foreign keys probably are going to be indexed. We create an index where the values are widely dispersed, meaning their SSN is good. Address is pretty good. Phone number is pretty good. Zip code is bad. It will return lots of values. So we want a field where the values are, I say here, pretty much unique. We like small fields. We can get more fields into each node of the index. We like data that don't tend to change very much. And if we go back up here to this thing and we consider what changing one of these things would be, it gets very expensive to change anything in this tree. We don't like data that change. Okay. Do not create indexes on primary keys or unique fields. Next. I believe we got it there. Okay, questions?
I'm good.
Well, I don't believe that I have really covered the binary tree, the B plus tree, very well, but it's a little bit beyond our class. And if you take a major in database at a four-year college, you're going to go into B plus trees in all of their gory detail, and it's not a pleasant experience in some ways. They are monstrously complicated, and just working with them is very difficult. Let me point out a couple of things about them. Previous, come on. Okay, the thing about a B plus tree is that it always has a flat structure. So this one has one at the top, the second level, and then the third level takes you to the actual data. And that's real common to have a three-level tree. You don't ever find a B plus tree that gets radically out of balance. It is also called a balanced tree because it is always a flat tree, meaning that all of the nodes in it tend always to be full, and you don't get this one limb of the tree extending out down this way. They will always tend to be nice and flat. I would have to teach a class on binary trees before that makes a whole lot of sense. But basically, I can always get through the tree in the minimum number of disk pages. So each one of these guys is a disk page. So this is a disk page. Let's say I had to access this one. This one is 5 milliseconds. Now chances are this one's going to be pinned in memory, 5 milliseconds. Boom, one more, 5 milliseconds. Boom, one more, 5 milliseconds. So in 10 milliseconds, I get to the data, and now with one more disk hit, I get there. So if I have to access root, that's 5, 10, 15, and then I go straight to the data in 0.2 of a second, which actually it's going to be a lot less than that because some of those are going to be pinned in memory. So the idea is that with a binary tree, even though I spend a lot, an index costs me a lot, in terms of maintaining the index and the disk space. Indexes are not free. Indexes cost me, but indexes will speed up my access time. If I choose my indexes poorly, and I build indexes on things that I have no business building indexes upon, then I will actually hurt my performance. So, for example, if I have a database, and in my database I have all of the people in Texas, and in one of the fields, I don't know why I would have this, I'd get in trouble if I did, but one of the fields in my database for all the people in Texas is gender. Well, about half the people are going to be one, about half the people are going to be the other, assuming a binary gender. We're not going to get an argument about that. If I search on that field, what I'm going to do is I'm going to use the index, and I'm going to search down through the index, and it will actually slow down my access to the data. I would do much better just to not have the index and to just go to the table and just plow through the table brute force and accumulate all of the males or all of the females, whatever it is I'm looking for. I would do a whole lot better than to use the index. So in many cases, lots of cases, if an index is chosen poorly, it can actually slow down your access time. Okay, so you use those guidelines. Those guidelines are important. When do you index? You index when you care about it. You index when you're going to search on it. Why do you index? Because you're going to search on it. If it's a primary key, it is already indexed. That's important. So you're going to search on your primary key mainly. If you want something else indexed, you can index that. Okay, so you care about it. Number two, you build an index when it has a very small number of unique values, meaning something like date of birth or something like that. You index on as small of a value as you can. I like things like Social Security number. I do not like things like the abstract of an article or something that will be big. And finally, I do not like things that change. Every semester, we have the 12th class day. What happens on the 12th class day? Well, I'm fishing for an answer that you don't know what I'm fishing for. So I'm just going to tell you. Go ahead.
That census.
Census, yes, census happens. 12th class day. Oh, why do they do it on the 12th class day? Again, I'm fishing, so if you don't want to answer, I'll go ahead and give it to you. They do it on the 12th class day because before that, everybody is changing from one class to another very rapidly. So on the 12th class day, they have to finally say, okay, guys, you're in the class. If you drop a class before the 12th class day, you were never in that class. If you drop the class after the 12th class day, that class will appear on your formal records. Gee, why is that? It's because before the 12th class day, up until the 12th class day, everybody is changing classes. They're adding classes, they're dropping classes, everything is in flux. What the database does is they go in and they drop all of their indexes. Dropping an index, by the way, is just as easy as creating one. I didn't mention this, but if I were to where did I create my index?
If they're easy to drop, then why is it so difficult to maintain them? Because you had said if you want to update something within an index structure, that's a problem.
Thank you for asking that question. Are they easy to drop? Okay, are they easy to drop? Oh, yes, they're easy to drop, just like it's easy to leap off of a 20-story building. Is it easy? Yeah, until you get to the sudden stop at the end. So
I didn't realize that was sarcasm a moment ago. Sorry.
it's easy to drop an index. I can drop an index. I just say drop index name. Oh, boom, bye. Yeah, I can also disable an index and not use it and not drop it, but it's just about the same thing, really, because I have to go back and rebuild it. Now, when you rebuild an index, when you create an index, oh my goodness, you can very easily shut that database down for 45 minutes to create an index on a large table. So dropping an index is very, very easy. You just drop it. And this is why on the 12th class day, they shut the database down, they kick everybody off of it that night, and they go in and they create all of the indexes. Creating an index is a very expensive proposition. Creating an index will probably pretty much shut down the table. Many databases, I don't know where SQL Server falls in this. I think it'll probably create them without shutting down the database. But for the most part, many times if you don't have to, you probably should take the database offline. In other words, kick all your users off and don't let anybody be in there doing anything, and then create the indexes, because it is such a huge undertaking to create these guys. Dropping them is easy. Okay. And that's why we do it on the 12th class day, because on the 11th class day, or the 12th class day, whatever, at 2 a.m., everything shuts down and nobody can log into the database, and they go in and they're working all night and they create all of these indexes. Now you cannot drop a class anymore. Now you are in the database, and now you cannot be deleted from the database. You are there. For generally, when you have an index, it gets tricky to delete you. It becomes very difficult from a database perspective to have a database, particularly with indexes, that is shrinking. We don't like them that shrink. They should grow. Indexes always grow. And there's a whole another hour of lectures on how indexes grow, how databases grow. And as they get bigger and bigger, how is the memory allocated to them? So databases are designed to get bigger. Indexes are designed to get bigger. They don't shrink very well. But what do I want you to come away from this with? I want you to come away from this with the important points. They're the ones that will be on the final. So if you take the final, we index 1, 2, 3, 4, 5. 5 points. With me. And so you couldn't hear anything on the 2 Ronnies, huh?
Well, that's not to say we can't go listen to it after lecture.
Yeah.
No worries.
My phone's ringing. Yeah. It's kind of funny. I guess my wife will get that. Yeah, it's a funny. I think it's worth watching.
It has a Monty Python sound or Stephen Fry.
Yeah,
Fry sound
it's
to it.
Monty Python-ish. Okay, well, let's see. It is time to wrap up here. Let's see the next class meeting. We will do the final. So let's see, what have we got? We've got the final one on, let's see, Thursday, the 6th will be the last module. On the 8th, August 8th, I will bridge into the next class. In other words, I'm going to talk about things that are not in this class. I'm going to talk about creating variables. I'm going to talk about if, then, else, and stuff like that. Next class, I'm going to try to do the, Tracy had mentioned the IIF and the case. I'm going to discuss those because I think they should be discussed, even though they are not part of SQL proper. They are part of SQL Server. Basically, IIF allows you to put an if-then-else statement into an SQL statement, which I don't know whether I agree with it or not, but since everybody does it, we're going to go ahead and talk about it. So I'll talk about that next class period. I did not assign that. Okay. Well, I guess I'll see you on the 6th.
Thank you. I sent you a small question.
Go ahead.
But it's no hurry. Well, no, I sent it to an email. I can't figure out a means of doing something by an inner join.
I haven't looked at it. I see I have a couple of emails there. I typically don't open email when I have my screen shared because I might end up sharing something that somebody thinks is private. So
no worries. Okay. I just mentioned it.
I'll take a look at it and get back to you right away.
No hurry. You have a private life. Thank you.
Well, my wife has just come off of the infusion therapy today, so I've been changing an IV 5 times a day, but now she's gotten off of that and everything's a whole lot better.
That is happy news, and I'm sure everybody in class is hoping that, for quick recovery for her. Happy to hear it.
We're doing very well, and thank you for your thoughts and prayers. Okay.
Thank you. Have a good night.
We'll see you next time. Bye-bye.